And I'm very happy and honored that these guys here are on this show today. I'm looking forward to it myself, and actually they're going to show us what machines do when they start to communicate with each other and influence each other. I'm looking forward to what Ting-Chun Liu and Leon-Etienne here to have to talk to us, have to show to us. I expect some nice images as well. I expect some nice insights in what these machines all do to each other. Please give a warm welcome to our new guest here.
Hello? Hello? Can you hear me? Oh. So today we're going to be talking about self-cannibalizing AI, which is a fancy word for recursion. And we are trying to approach different artistic strategy to try to understand, expose, exploit somehow text-to-image models, specifically Stable-Diffusion. But we did have some experience in all other text-to-image models. So let's start with something like this. What happens when AI confronted an AI-generated image? We start by having image-to-image model running, and then once we put the output, we put it in again as an input, and we see something like this. It's colorful, random, purplish pattern. And then we start wondering, what causes this? Why does it go pink? Why does it have a certain pattern? And does it have something to do with the initial image we input? And then we did more tests. We had a lot of stock footages, and then as the initial image, we ended up having more and more purple, or more and more purplish pattern. And this begins our journey to try to understand what it actually is Stable Diffusion or these image generation model. How is the architecture behind it, and what causes this problem, or not even a problem, it's aesthetically nice looking, but what exactly happens there?
Yeah, but before we dive into Stable Diffusion and other models, we first want to introduce ourselves. My name is Leon-Etienne. I'm a computer scientist and media artist based in Cologne, and I mainly focus on stuff like no prompting, like prompting without prompts, or feedback systems in artificial intelligence and data visualization. These are my main points.
And my name is Ting-Chun Liu. I'm also a media artist and half-baked programmer. I want to start by briefly mentioning my own project. I'm doing a lot of beach images that were generated based on different various artificial intelligence models. And throughout history, we see all these interesting social media beach images that ended up having clear sky, white sand, nice-looking, beautiful structure. This is caused by human-made bias because all these beaches that are online are usually the one that you see on social media. So we started by talking about biases. And this is a really interesting paper trying to deconstruct all the biases that happens into the machine learning models. It's important to notice that we oftentimes think of biases being resulted by data, but it's not only data, because throughout the whole training process, some other bias could have happened during everything. You could see that if you train the data in a certain way, you will result a different bias. If you generate the image or generate the text in a certain way, you will also result in a certain bias.
So, and why do we talk about AI? I mean, biases, there's lots of talk about it. Please don't quote us on this. This is humoristic. It just sums up the development of AI and how the hype is perceived. And we just want to emphasize that even though we are talking about AI, all the problems that we show of biases, of recursive pipelines that feed from one another are problems that happen in all of software development. So it's not only AI, but the interesting part for AI is we are right now, it feels like we are on this top peak of the high AI hype, and it sometimes feels like there's this linearity of progress that we started with, like, I don't know, the Turing test in the 1940s, and now we have ChatGPT, and it feels like this is this one continuous upwards thing. This is what lots of marketers want us to believe, but what we want to emphasize is that for us, especially like the text-to-image models, it feels purely accidental. It feels like we look at one very particular branch in the tree of papers and development. We look at this one particular thing that kind of works right now. And like probably 5 years ago, if we would have held this talk, we would probably have talked about GANs, like generative adversarial networks. But right now we are talking about diffusion models because these are everywhere. And this is right now the hot thing, but kind of accidental.
We want to start by explaining our artistic concept. We want to cite Avin Lucier's I'm Sitting in the Room, which he did a sound work. He had a tape machine and then recorded in I am sitting in the room and then do a playback, and has another tape machine to record and then play back again, and doing this back and forth. In the end, you get something like a white, noisy sound. Or like some people might have tested, maybe, to have a printer, you print out a random image, and then you scan it again, print it again, scan it again, print it again. You ended up having a white noise, whatever that is image, is usually white. And we were thinking about Shannon's communication theory about how noise source was affecting the output source throughout the input. And the really interesting thing is that when Avin Lucier was trying to measure the sound or the reverb of the space, he's using feedback mechanism. And we're trying to use the same mechanism to understand this space, which is the Stable-Diffusion or the latent space or the embedding space. We deconstruct the whole pipelines and try to run in different components with our different feedback strategies.
So before we show you more colorful images, we have to talk about what kind of Stable Diffusion is, or what this is. I mean, lots of you have probably used it, and it feels like it is this black box where you input text and then you get an image out of it. And it feels like, when I first heard of it, I was thinking about it as this large neural network that has like text input and image output. But actually, if you look into the pipelines, and these are like different representations of the pipeline, what Stable Diffusion is actually doing. On the left, a mathematical one. In the middle, one that I found on Hugging Face, which is like this flowchart. On the right, it's code. There's this one particular part that's very interesting for us, because it's a loop structure. So like the process of text to image, it's not this one-to-one relation, but there's this thing that goes in a loop, and it goes towards something. So there is already feedback in these systems. So us using them as feedback systems is kind of ironic, because we use a feedback system against itself. And one other thing that's very interesting about this pipeline is you see it's very complicated. All things are complicated, that's true. But like there's different steps in this pipeline that come from different models. So there's multiple machine learning models working together. So it's not only this one text-to-image model like you sometimes are ought to believe. There's actually like very, very different parts of the machine that go together. And there's this great thing on Wikipedia where you can see in this graphics, on the lowest layer, on the orange box, these are the things that we know. These are on the application layer, the things you can use in your browser. These are the apps where you input text and you get an image out of it. It's like Midjourney, Stable Diffusion, DALL-E. I think you probably heard of them. But the funny thing is, it also shows which generative models are used, and also what is used to embed the text, like how the text is processed. And what you can see is like all of the things we use right now, they go back to this one model called Clip. And when we first saw this, we were like, well, what is Clip? We kind of have to look at it, because it's in every single application that we use right now for text-to-image. And the other thing that's very interesting is if you look in the top most row, there's also dataset, and there's like one dataset. Not one dataset, but there's like Lion 400M, but it's variations of the same dataset. So there seems to be one model that's used throughout most text-to-image models, and also one kind of dataset, or one provider of datasets. And this should make you curious to see what is in this dataset, and also what is this model, Clip, that is used throughout.
Trying to go back to reinforce the idea we were mentioning about the accidental thing that happens in the current AI image generation model, is these models are the backbone of all the models we're using right now. And this is accidental. They could have been other models that could be the backbone of anything. So what this means is that if we investigate this model enough, the bias we see inside could be the bias of most of the image generation model. So we dug a bit deeper into what exactly Clip is. Clip, To simplify it, you could input a line of text or keyword and then an image. And inside of this model, it finds the correlation or the distance or a similarity score between this text and this image. As an example, we input the keyword happy, and then we input 2 faces. These faces were created by this person does not exist. It's the AI generated faces 5 years ago, which was not the whole diffusion thing. Which face has the higher correlation or looks happier?
Vote now.
Left? Right? We ended up seeing that the right side of the picture has a higher similarity score. But what about these 2 images? Left? Right. Well, the right side is the happier image. But what does it actually mean? Like, what does it have to do? What does this score mean? Like, now we have a model where we input a keyword and then an image, but we ended up having a number. And this number brings the possibility that we could calculate distances, correlations, relations, and probability. And this became the backbone of all the image generation model, and it's creepy. Just a bit context to it. CLIP was created by OpenAI, but before that, there was a paper about a medical journal that they were trying to find correlations between symptoms and X-ray images. It makes a lot of sense because they want to understand does this X-ray image has a higher correlation, a higher possibility that it ended up in the certain symptoms. And thus, OpenAI create a CLIP. They input a tons of data, a tons of image, a tons of text. It's important to notice, at the time, they were not planning to do an image generation model. This wasn't the plan. This model was built to do image recognition. And it's a new way to do image recognition because it's not like finding certain components or finding certain details in the image. It's just feeding an image and finding correlations to the text. They tokenize the text and also tokenize the image, and then just find a certain relationship in this high-dimensional space. One of the use case, which some of you might already experience, is the not safe for work filter in Stable-Diffusion. They also use CLIP at the endpoint. Once you generated an image, they will run through CLIP, and then it's really funny that they use this 17 keywords. And once one of the keywords has passes the threshold, it will trigger the not safe for work filter. And this is extremely problematic because, as we said, this keyword is just a mathematical representation of the correlation. It doesn't really semantically mean anything. And for example, we will see a lot of false positives, like the photo of Donald Trump jumping into the pool will result in a trigger from the filter. And some random abstract image may somehow has some components inside. When going through CLIP, it also triggers the not safe for work filter. So we start by doing some experiments. We were thinking of if we put a lot of this person does not exist, and then we run through the scoring system with the happy image. Will we ended up finding the happiest person from this person does not exist? Okay. Ooh. So. Yeah. Quick demo. So on the left side, you will see the picture that we in real time downloaded from this person does not exist. And on the left side, this is currently the lowest score of the photo, and this is the higher score. And you see that throughout a lot of different iteration, we will ended up sort of seeing the most happiest person. Right now we have someone like this, and the most unhappy. It's not the saddest, it's unhappy, or like the farthest, or having the most distance between this image, the keyword happy. Okay. Oh, there's another one. Okay. Let's continue. Okay, so now we go into a really interesting question. So now we input the keyword happy, but what if we put other keywords? And then we put different stuffs, and then also run through stock footage. And we have our friend Pedro here. It's funny because it doesn't make sense, but it somehow also makes sense, I guess. But just to keep in mind that this is a really, really important point that we're trying to express. This clip model is the foundation of most of the image generation model. So if we have a woman as a higher score in nurse, definitely in the image generation model, we could have that generated. And this is the danger that we are trying to propose. And also at the same time, they are a certain artistic quality that they're looking for, like a grape is not art at all, but a random firework has a higher correlation to the keyword art. And thus is the bias that we were proposing. And then we ended up inputting different keywords and then do like a softmax comparison between them. This random AI-generated face has a really high similarity score to Aboriginal Australian. And also this image of schnitzel has a higher probability between Chinese and European. It makes sense for us, but this is us putting our own bias onto this image and onto this mathematical space.
I think one thing that's very important, this list of ethnicities, we took it from the US Navy, so it's not our list. We didn't make a list of ethnicities. We just Googled for one, and then the US military surely has one, so we just used the US military ethnicity list that you can, when you enlist, cross in which ethnicity you are.
And we put other stuff. It's funny because as a human mind, it makes somehow some sense. But this is the bias that we want to talk about. We are inputting our own bias onto these machines and onto these models. So we put our own faces also. And we put a list of different countries, and then we ended up having the higher score of which name of the country that has a higher correlation to us. And it's funny because we found something called Chad. Oh, I mean, we have to go back to talk about again that it's not a homophone because it's really interesting that mathematically this keyword Chad has double meaning, but at the same time it's us as a human to understand what that means. For the math part, for the latent space, they don't really know. And we try to contextualize it. If we input the keyword with a sentence, in the beginning it says person from the country Canada or person from the country blank, then we ended up having a more proper result. But by proper, I mean it's biased. Also, we put food. It's good that we use our own face. But that's the point that we want to try to emphasize. Like, what exactly is this model doing? And this is the backbone of everything. So now we understand that if we have enough faces, and then if we go through enough iteration, we ended up like finding the happy face. But the most happy face, again, is just a higher similarity score to the keyword happy. But how about generating a happy face?
Yeah, thanks. If you remember when we tried in our live demo where we tried to find the happiest and the furthest away from happiest person, we used thispersondoesnotexist.com as our generator, which just gives you random faces. It's admittedly a very stupid generator. It just gives you a random face, and then we look, is it a higher score, and then we keep it or we throw it away. So we already almost built our own text-to-image model because we can input any text, and then with lots of iterations, it will find a face that kind of fits our description. But like the interesting part is also like we can generate this image on the way by using kind of this similar structure. So kind of we build our own text-to-image model, but Stable-Diffusion is a bit more complicated. And we shortly have to go over this slide again. I always find it very funny to look at all of these different representations, because, I mean, we can look at all of them and not understand them. I don't understand them. But at least I found the parts that kind of made sense and are like similar things in these different representations. And there's like different steps that are kind of important or like happen in the pipeline that I could kind of make out in all of these representations. And the first one is that we need to embed the text, which just means you type in a text and you get a very high dimensional vector that you then can calculate with. This is what clip is used for that. So that's exactly what Ting showed you beforehand. And then the second part is like the actual diffusion, where the image gets generated, and this happens from noise. So we start with like some very colorful image, and then it slowly over time generates the image, trying to follow the text that we input, like mathematically. And then in the end, because I lied to you, all of this doesn't happen with pixels. It happens in some abstract space that we can't see. It has to be converted back into something we can, so into pixel space, and then we have the finished image that we can actually see. And
I want to sort of emphasize again on the embedding part. This is a really important thing that we need to think about. How do we embed the keyword happy into a number? Because we don't, as a human, we have emotions, and these emotions are currently being embedded into a strings of number. This really doesn't make sense. It don't really align with our sentience. But this model works solely because of that, because we could embed different types of keyword into numbers, and then it generates the image.
Yeah, that's very important. Once you have typed in anything, all the meaning is gone. It's all actually bits and bytes. So all the meaning we put into it, if we use text-to-image models, is like the things we perceive. So we put meaning back into it again. And this is like this process. It's also called reverse diffusion. What's very interesting is like the current image, the one on the left, is like the current state of the image. It's an iterative process. If you ever used prompting, you can type in steps. That's like the steps of diffusion it does. Then the thing in the middle, this is actually the thing the model learns, which is just noise, how to generate noise. And the right image is then what it predicts the image will look like. So it's basically the left image plus the noise in the middle equals the right image. And you can see like over time, it slowly goes towards the concept of dog. And this is like happening in a loop. So like step for step, it generates new noise to go towards the keyword, for example, dog. And this is very important. Like Stable Diffusion does not generate images. This sounds weird, but it's actually a very, very sophisticated noise generator. So it generates the thing in the middle. And the interesting thing about the architecture that they used, because we already heard that clip comes from like the medical field, the UNet structure that generates this noise in the middle also comes from the medical field and was used to segment also X-ray images. So maybe the most advancement was not OpenAI, it was medicine after all. And what's interesting in this process is that you can also say how much should it go towards dog, for example. And you can also, in the code, just like comment out the line. Like just don't go towards anything. Just do your thing. Just denoise it. Like just add noise over it and see where it ends up. And this is what we did here. We just cut out the part where it goes towards a concept and let it like denoise itself and see where it ends up. And it's very funny because you can still make out things in there, even though there's like no guidance in there at all. And this is probably the rawest representation of like the latent space, of the raw data in there. Probably the couple down there in the middle is somewhere in the data set. And if there's no guidance, it can just reproduce these patterns and things that are normally not seen. You can also do the inverse. So say, instead of going a very small number towards cat, you can also like do it times 1,000 and get like the cattiest cat, which is even for us not the cattiest cat. But here you see from left to right, top to bottom, we just increased this, go more towards the keyword cat, and you can see very fast it gets outside of our realm of understanding what a cat is. But now back to how did we do these red images, because this is one of the main topics of our talk, is you probably have used image to image, which is the same as text to image, just instead of an text you input an image. And what you can do with this is you can give it an image and then you describe it in a prompt. I want to make this drawing into some fantasy landscape, and then you get a fantasy landscape. But what we did is we input an image, also stock images again, and we didn't put in any prompt. So we just said like, do your thing without anything. And we wrote a small little library that's very shitty, so please don't read the code. And just did this in a loop. So we said, take this stock image, do your thing. Then we took the output and we put it back in again. And I mean, we already spoiled you about this. It turned very pink, very quickly. And we were like, okay, how can this be? Is this like a floating point error? Do we have to, I don't know, change like some parameters around? So we just tried again with different models. And it turns out different models, these are like in the order of their release, Stable-Diffusion 1.5, 2.1, XL, and XL Turbo, like the main versions. And you can see all of the models converge into something, but they all have their own favorite color. So choose your spirit Stable-Diffusion model now. So Stable-Diffusion 1.5 goes into this weird, colorful purple patterns, like Stable-Diffusion 2.1, more like primary colors, SDXL, straight lines all the way, and architecture. And Stable-Diffusion XL is like this turquoise photography. I can't even describe it. And we were still curious, like, okay, this is still like some calculation error. We are doing something wrong. So we tried it again. There is the strength parameter. So when you do image to image, you can say how much of the original image you want to keep. And so we tried it, like 0.5 is like the base thing, so it does like 0.5 your image and then noise on it. And we tried it until 0.8. And even at 0.8, you have to imagine it generates lots of new stuff. It still has their favorite things and patterns that it kind of converges to. And funnily enough, Stable-Diffusion XL just likes architecture so much, it can't get away from the windows. And Stable-Diffusion 1.5, it lost the pink and turned black and white, but it's still the same kind of patterns. And interestingly, Stable-Diffusion XL, you see this bird and this butterfly, they come all the time. Like they, probably it's some XL training problem, but it's something that repeats over and over again. So we were looking more into the code, and I told you about before that all of this stuff doesn't happen in pixel space, so it's not really pixels that we're dealing with, it's like encoded into some mathematical space, and then it's decoded again into something we can see. So what we did is we used this encoder, which should do nothing. So you take an image, you encode it into this latent thing, and then you decode it again. And we did this in a loop as well. So we put the output back in again, decode, encode, decode, encode. And funnily enough, yeah, sure, it was not able to reproduce the image perfectly, which mathematically probably makes sense, but still results in these very beautiful organic patterns that look similar to the Stable-Diffusion 1.5, I have to say, but still have like their own distinct noisy quality, and kind of show probably how this and what this autodecoder does. You can see there's like this smoothing happening, so it's probably like summarizing pixels together. And to kind of now rule out that it's like a Stable Diffusion thing, we used DALL-E as well. So we used Stable Diffusion and DALL-E, and they're playing Stille Post. So we let Stable Diffusion generate one image, we give it to DALL-E, let it generate an image, and we put it back in again. And we do this in a loop. So they communicate with each other with images. And funnily enough, it does not turn into pink noise, but you can still see, we started with random photography stock images again, it still devolves into some noise. So maybe it's like floating point errors in both, or there might be something that's inherent to these diffusion models that have the inability to reproduce images like they were inputted. And the other thing that we did, we didn't stop there. We used the Stable Diffusion upscaler, which does, when you give it an image, it just upscales it 4 times, and then you have a higher image. And what we did is we upscaled an image, then we downsampled it again, like manually, not with AI. We just put it in Photoshop and made it small again. And then we upsampled it again. And then we did this also in a loop. And funnily enough, we tried like different methods because we were sure, okay, it's some calculation error, but no matter the thing, no matter the parameters, no matter the input image, it still gave us these very beautiful yet non-existent patterns, which just shows that it was unable to reproduce the image completely, which also still has like these very organic qualities, which probably say something about the algorithm behind it. The other thing we did is like we tried to play Stille Post again, and we had like 2 models against each other again. This time it was text to image and image to text. Text to image we all know, but there's also the inverse, which is image captioning, actually, like the research term. And what it does is you give it an image and it tries to describe it. In this version we used GPT-2, I know it's very old, and Clip, and we started with an image. You see here like the photography of like the ocean, and then we made a text out of it, so it made a large body of water with few surfers, and then we turned that back into an image again, and we wanted to see where this ends up. So we did this also in a loop, and we found that even though it's not pink patterns, there are still like some things it likes a lot, like trains. Yeah, trains. So it got stuck on trains, it got stuck on trees, then fire hydrants, probably because they have this very nice red color, brick walls with clocks on it, lots of clocks, then dogs, sure, the internet has a lot of dogs, also benches, it likes benches, and yeah, lots of things, but still like the same reoccurring things. It was always the same things repeating over and over again. Then it went back from cats to dogs to fire hydrants, so it was always repeating the same things. Oh, there's bear and brick walls, I forgot. This is probably a thing with the image captioning, because the image captioning is GPT-2. It's probably not too good at like captioning images. We are not sure, but there is something reductionistic about these systems that's kind of funny. We then kind of found a model that was able to reproduce an input image almost perfectly. It was realistic vision 0.5 or something, so like some very specific model and some very specific parameters. And if we put that in, we were able to like almost reproduce the image. You can try for yourself, like the left image is the first image, and in the middle one is the new image that it was able to reproduce. And on the right, just for visualization purposes, I put the difference between the two. For us, I would say it's kind of the same image. But the interesting thing is, if you do this in a loop, and we did it like 16,000 times in a loop, you can see that from time to time, it still changes a lot. It goes towards horses, it turns black and white, it will also show lots of wedding photography and architecture. And I'm sad we don't have time for this. This goes on for like 10 minutes. But you can just believe me, it will not... It will not stop at one thing, and we look at it in slow motion to see like where does the faces come from, where does it come from, and you can actually see if you look closely enough that sometimes a face disappears into a lantern, for example, and going back to the thing again of like the mathematically equivalency. Oh, there he's gone. They're back again. So people disappearing and appearing, like the change is that there's like, even in the image, there's like a mathematically ambivalency at one point between, for example, a lantern and a face. And it doesn't make the distinction between the two. So from one frame to another, it's a face. And then it keeps the face, and then the face grows a little bit. And funnily enough, the method we used here is kind of also how these animation frameworks that you see online work. They kind of also work like this. On the right, you see a map. And what I tried to visualize here was going from a program from David McClure, who took like, I think 12 million images of a data set and also used clip and put them into a map. And I wanted to see like where it travels. So I tried to find the closest point to this image on the left. And you see it's like super chaotic. So the machine sees like very different things from frame to frame. And it's not, for us, not very easy to follow. So we kind of have to go back to the data again, because now we talked about the algorithm, and it kind of shows, okay, there is problems with the algorithms, but maybe it's also a data thing. So we looked into like what Stable-Diffusion is trained on, and it's trained on a data set from Lion. Lion is like a non-profit. Maybe someone from Lion is here. Let's talk later. That take Common Crawl, which is like just slices from the internet downloaded, and they go through these slices of the internet, like these archives, and they look for images and their alt text, like their description. And then they collect them and curate very large data sets. And in this data set, you then have just the URL, a description of the text, and then some parameters. And funnily enough, you don't have to read all this on the left. The only important thing here is that you see that there's like, even the training process is like a very complicated thing with feedback in it. So there's like different steps with like different parameters. So it's not this thing we just throw the data at it and then it learns. It's this very iterative process of adding layers of data after each other. And one thing that's very interesting is like these parameters here. They're called pun-safe and aesthetic score. And PunSafe is just the not safe for work score. So they also filter out some not safe for work images, and we showed you in the beginning how well that works, so probably there's some stuff missing in the data. And they also used something called aesthetic score. And aesthetic scoring, what this actually means, like Lion themselves, this is no front to Lion, I'm sure the closed source people do the same thing, so at least we can read about what this does. It is the question, how much do you like this image on a scale from 1 to 10? This is the aesthetic score. But they didn't do this by hand, because the largest data set has 5 billion images. So they trained an AI to do it. So they have an AI that actually takes one image and gives you a score between 1 to 10. And how they trained this is they took like images from DP Challenge, which is like a photography forum, and also from some Discord where people could rate their own Stable Diffusion generations from 1 to 10, and they trained a neural net on it to decide for a score. And this is a website that is public. We can also, and we can do this live. We can aesthetically predict ourselves, which just gives you a score. Okay, the sad thing is if you are below 5, you are not in Stable Diffusion. So I'm not in Stable Diffusion, but it's probably the lighting. And we have to remember this also uses clip, so it kind of works with clip as well. So you have to also consider the whole image, like it's the lighting, it's all the thing, it's the contrast, if it's drawn in watercolor and stuff. Because if we look at the actual slices from these data sets, we can see in the lowest tier of this data there's like lots of logos and memes and stuff. So it kind of learns something. But if we go to the very high tiers, we have to scroll some time. You will see lots of artworks, like most of them are copyrighted. This should be obvious. And if you go to the very highest score, it's like mostly stuff painted in watercolor or acrylic and stuff. So it learns something, but maybe only the correlation between aesthetic score and watercolor paintings. But it is at least something. That this is problematic, I mean, I don't think I have to point that out, but we can just look at it, because I took a subset of Lion, the top 0.05 most aesthetic images, and I also used the code that I showed you before into a map, so we can shortly take a glimpse into this data space. This is a whole nother talk, so I have to go very fast. So this, what you see here is like 650,000 images, and you can color them by different parameters. You can, for example, look at like not safe for work images. Color scale is not the best. Blue means high, pink means low. And there's one very interesting correlation that happens here is if we look at most of the very high scores for not safe for work, it's mostly like female stars. So it probably learned something very sexist that is definitely in all of the data sets. So probably because the correlation between the words that we showed you before, like nudity, etc., is because it learns from the internet, has probably picked up on these being used derogatory for female stars. So it kind of has learned this probably. So I can, all the blue parts, it's mostly female stars. And the other very important thing, or very interesting thing, is that I looked in one of these clusters and found some Star Wars images, also some memes. All of these images are downloaded like live, because if I would download them beforehand, it would probably be illegal, so we are all illegal together. And I was wandering around the Star Wars cluster here, and then I saw this weird outline here, which was all images of the French chef Paul Bocuse, which is like a famous, very famous chef from France. And I was wondering, why is he so close to Star Wars? Is this some weird correlation that I have not picked up on? And there actually is an explanation. We can explain it right now with the mouse cursor. So we start with like some Star Wars over here. So Star Wars is now owned by Disney, and Disney has like Disneyland. And in Disneyland there's Galaxy World, I think it's called, which is like the Star Wars part. And but also in Disney World they opened a new part of this theme park, which was about the movie Ratatouille. And in there's a restaurant, and in this restaurant, on the opening, who was cooking there? It was Paul Bocuse. So the yes. So somehow Clip has picked up on this very weird coincidence of like relation between Star Wars and Paul Bocuse. So the next time you do Stable Diffusion and you generate a Star Wars image, if there's in the background someone looking like Paul Bocuse, you know why this is the case, maybe. Yeah. I think, we're kind of coming to the end of our talk because we talked now about, like, this is kind of silly. Like, we used algorithms against what they're usually meant to do, which is also very valid. You should always try to do that. Like, misuse is also a very good use. But is this actually like something we should worry about? And I found one example. It's called Open Journey. It's a Stable Diffusion version that learns from exclusively, or is fine-tuned exclusively on mid-journey images. So it's one Stable Diffusion version that learns from another generative AI. So kind of these feedback loops kind of are happening. And there's actually like some research about it, and they call it now model collapse. It's very new, and it's a new fancy term. It's what happens when artificial systems, especially generating ones, learn from also at artificially generated stuff. So artificially generated images, for example, or also for artificially generated texts for large language models, for example. So this is actually these feedback systems that are now we used in a silly, fun way. It might actually be something that could happen in the near future.
So we want to go back to the original thing that we have with the red image. And this is a really important question as a metaphor, or even as a hypothesis. At the time, it was early this year when Stable Diffusion 1.4 was on, and once we were generating image, we heard that, it could be a possibility that all the people were generating image, they posted it online, and then throughout the years, they will be trained back again. And if this iteration happens again and again, will we possibly ended up in the internet where everything is purple? We don't know. Could be. But this is more or less a hypothesis or a metaphor that we're thinking about, because as we previously mentioned in Clip, or in all these different models, we all have certain biases, whether it's visually appearing or it's not. But if we keep on working with these models, somewhere we ended up in a certain, I don't know, the green pattern, the architecture pattern in our internet images. And this is how we want to end our talk here. So thank you. Yeah.
Super work, guys. Really fantastic. I guess we will have some questions here, isn't it? Yeah. No? Shall I do one? So how did you do this with the live images that you just captured? The live images you just captured.
Live image?
Oh.
I guess so.
What?
We're going to have some questions here.
Yeah. Okay.
Good. Number one. Also.
Hello, and thank you. I was just curious on the feedback loops that you did running images through the same model again and again. I only saw that you did this with like general purpose image generating models. Did you also try and do this with like LoRa's or fine tunings or models that were made to do specifically cats or something?
Mm-hmm. I mean, actually, the movie that you saw is kind of like the model we used, realistic vision, I would say is kind of a fine-tuned model because it's already fine-tuned on these very high realistic stock footage images. And this is probably why you see lots of like brides and grooms and stuff like this, because it's kind of fine-tuned towards these images. So it kind of showed very similar images to the images it was trained on. So probably we didn't do it like for a very fine-tuned model, but it would probably also repeat the same things over and over again.
So it would be fair to say that you find like what you'd expect there.
Probably.
Yeah.
Yeah.
Thank you.
Good. Here, number 3, please.
Yeah, we are at the chaos congress here, right? You remember probably the 80s with the chaos theory, Mandelbrot, Apfelmännchen and all this. And there was this attractor concept. So you have an attractor, and that sounds pretty much like this. Did you think about the connection between chaos theory, attractors there, and what you do?
Kind of. When we first talked about these concepts that it would fall into, we talked to them, we called them sinks, like something it would go in and like never get out of it again. Because in one of the first things we tried, would always end up in images of toilets and bathrooms with sinks. So we kind of made the connection between sink and sink. So we kind of imagined it as this hole in the possibility space that it would fall into and never get out of it again. But throughout the experiments, we are not too sure if it's really an attractor that it can't get off of, or if it's just more like a computational artifact. So we're not really sure if there is like we're missing out on stuff and it really falls into a hole, or if it's just a plane, like it's always there. Once you are below a certain threshold, it will always be this. Yeah, but we kind of thought about something similar. Yeah.
Here, number one, please.
Yeah, a fantastic talk. Thank you very much. You talked about what the algorithm might pick up and looked into the data. Have you looked into what the encoding before that was, like JPEG, for example? Could it be like it's picked up like glitches and like the weird encoding reminds me of like MPEG or JPEG colors? So have you looked into that?
It's a really good question.
Yeah.
The thing is that it did change because once when we were trying to investigate on the clip model, we did found that they had a certain way of doing tokenization based on image. So they ended up having all into embedding space. They made their own tokenization in their model, but we're not really able to crack it open. So, yeah.
And for the image part, my first guess was when it turned red, I thought it was like some encoding thing, like the red channel kind of, I don't know, is maybe more important. And that's why, I don't know, maybe in the variable autoencoder, for example, red seems to be more important, and that's why it turns into red, kind of. And maybe this comes from, I thought it would come from some color input or some format, but I mean, we tried with different models and it turned out to be different colors and different patterns. And I think it's more on a higher level of like abstraction, because like I said before, it doesn't really calculate in pixels. All this diffusion part happens in a latent space already. So the JPEG artifacts, they would also have to be encoded into this thing. Maybe there is like some latents that correlate to like these artifacts on a certain layer, but maybe not. Yeah.
All right. Since our signal angel is disappearing, okay, number one here.
Thanks for your talk. That was my highlight talk, actually. And so one understanding question: this image-to-text correlation model, this a clip, is this still actually used, or is it like something that was like a version before, or is it still used? I didn't understand.
It's still in use, and that's the crazy part because it works. So people just continue using it, and they were like fine-tuning or make it more efficient on all these application-wise model. But the backbone of Clip, because it takes too much manpower to actually create it, so it ended up kind of always there. There is, we didn't really mention it, but there's two different variation, which is Clip. It's an OpenAI product, but there's also something called OpenClip. And OpenClip did what's kind of funny is that they were trying to make it as much as Clip itself, but it ended up having the same structure. But it's the bias we talked about or the issue we talked about, it's always also appear in both of the models.
Okay, thanks.
Good, we continue here. Oh.
Hi there, great talk, great schnitzel. In the talk you showed how you rerun the encoding process, the encoding between actual RGB pixels and this internal vector space and what happens to like the visual image. Mm-hmm. Have you also tried running the generation process, like let it think without copying back and into RGB space, like running in cycle the generation in the internal space?
Yeah, I actually thought of it, but we never did it. But I had the same thought because I was thinking, okay, maybe it's a quantization error. It's something like on this way from latent space outside. But then I thought again, for our purposes, we kind of wanted to show that you can do this like drag and drop in image. This works with real images. For the idea of what is happening in the future, our future will happen in pixel space because this idea of model collapse and all these things, they will happen on the pixel level because all our images are in pixel space that we publish on social media. So we will get back to you very soon. And so we thought about it, but we never did it.
Okay, thanks.
Thanks.
Right. Signal Angel, was there some news from out of space? No. Yes? Oh.
Yes.
Then this was the... Yes?
Yes, we do actually
Good.
have 2 questions. I'll ask one. First, is the tool that you used for exploring the latent space available, or would you make it available to the public?
It's some code that's a Frankenstein code from like different GitHub repositories. So I would have to check the licenses again. And also, I'm not sure, like right now, copyright-wise, I'm not sure if I'm allowed to do this, because like all of these images are copyrighted. So when you hover with the mouse over it, the actual image gets downloaded to your computer. So I'm not really sure. So for legal reasons, no. But maybe when I looked more into it, you can find it online. I will tweet about it.
Good, that was the one question. You had 2, you said.
Yes, the other question is that the internet would like to know, as more and more content is auto or AI generated and put on the internet, and maybe feeds into future training data, if there's any way to protect future training from that.
There was, it's also happening early this year, there was some proposal through both Stable-Diffusion and I think Midjourney that they add a hidden layer of watermark. It's another research topic, and we did another talk a long time ago. It didn't really work that well because people tend to download their image and then they change format and then they crop it, they resize it, and then the watermark didn't really work that well. But I think there are research that are doing right now just to add more watermarks or like some hidden layers into the image itself to let some of the models recognize it when they're doing training.
Yeah, but there's one interesting thing about digital watermarking. If you want to not be digital watermarked, you can just take your image and use another AI to like reproduce it to 99.9%, and the digital watermark will pretty sure be gone. So, I mean, I think then we are in the situation that you have with hacking in general, like with video games, for example, where you have a new patch of a new version, and then you have some detector, and then you have a new version. So I don't think like digital watermarking will not solve this problem.
An open world. Please, there. Number 4.
So I'm a bit tired, but one of the patterns that emerged looks a little bit like the reaction diffusion patterns and the activator inhibitor. So maybe you recreated some dynamical system like that?
Definitely the upscaling one. Exactly. I don't know if we can go to it. Definitely is reaction diffusion, and I actually this is the why we have this slide with the different methods. Because if you see here, I know we skipped over it pretty fast, but this one we use different methods for like downscaling the image. Because if you think about downscaling, it could be the diffusive part of a reaction diffusion.
Exactly.
And this is what we thought as well. So we used nearest neighbor, we used all the different interpolators that you can use, and also used none. So we used nearest neighbor. So it still emerged as like these reaction diffusion patterns. So it's probably a reaction diffusion system because there's some diffusion when you downscale it, but
yeah, and also with convolution, like you get similar things if you iterate those. Yeah, okay.
Yeah, definitely.
I regret to say this, but this is one of the last talks of this Congress. Oh my God. Thank you guys. Thank you Ting-Chun, Louis, and Leon-Etienne for this fantastic presentation. Really.